To give you kind of a broad overview and introduction to the Hubble tension, sort of set up the next couple talks. This talk will be mostly based on work from two papers. One is a paper that Sylvia Gali and I wrote for the Planck collaboration a few years back, and the other one is the paper by the same title as this talk that is with Lloyd Knox from a couple of years ago. And as soon as I can advance a slide. So the outline of the talk is basically I want to tell you a little bit about just how do you constrain H0 from CMB observations. Most of my background is in the CMB, so this will be somewhat biased towards telling you things about the CMB. And then I want to tell you about specifically some things about the Planck observations and how those led to the values of H0 that we recovered. And then the end part of the talk is sort of meant as like a guide for observers and theorists, a Hubble Hunter's Guide, thinking about how do you actually resolve this tension cosmologically. So the reason that we're here, all the interest in this is because there's this basically disagreement between local measurements of the Hubble constant and other ones from the CMB and from the early universe. And so here we have a summary of some of these local measurements. They're all basically at some level based on just the Hubble's law, which says that that if you plot the distance versus redshift of distant objects that are in the Hubble flow, that the slope of that is the Hubble constant. And really, if you had just an exact measurement of one redshift and one distance to an object, which was in fact exactly in the Hubble flow, with that one object, you get the Hubble constant exactly without errors. Now, of course, things have peculiar velocities relative to the Hubble flow, so you need lots of objects to average over. Also, redshifts are, relatively easy, let's say, but cosmological distances are much, much harder. So these have big errors associated with them. And so you need lots of objects, various ways to measure these distances. And some of the ways like you see on this plot, for example, involve things like the distance ladder, where you calibrate distances using parallax to Cepheids, which you then use to calibrate some supernovae, which are then in the Hubble flow. There's a couple of things like this on this slide. There's other ones, for example, such as the holy cow measurements, which use strong lensing time delays, sort of to kind of implicitly calibrate these distances. But the bottom line is, and I won't go too much into the exact details of any of these measurements, but you do any of these things and you get what you see on this plot, which is things that scatter around 72, 73 with error bars that are on the order of just a few percent now. And so this picture is nice, but the tension comes from the fact that when you look at what you get from early universe measurements, you get these values here that you're probably aware of that are much lower. Here showing, for example, from the CMB, from Planck, from BAO, and I'll get into these. And these are sort of around 67, 68. And this difference, in fact, this stark contrast between what you get from the early and the late universe is the Hubble tension. So, how do the H0 constraints from the CMB side work? They're not quite as simple as the Hubble's law. So basically from the CMB, you can think about it in the following way. So the CMB, you basically use the Friedmann equation. That's not just the low redshift Hubble law approximation, but now over all redshifts, which if I drop a bunch of units and c equals 1 and write things out this way, basically says that H0 is equal to the sum of the matter density and the density in lambda and dark energy. These omegas, which if you're not familiar, this is basically, they're these capital omegas times little h squared, where little h is the Hubble constant over 100 kilometers per second per parsec, which actually kind of obscures the fact that these little omegas are purely just a choice of units. So this is really just an energy density a mean energy density of the universe in some particular units. And if you have this for the matter contribution and lambda, you just add these up, take the square root, and that's h naught. And the way the CMB measurement or inference of this works is that assuming a specific model, the lambda CDM model, you can infer what these two quantities are, and then you can get h naught. And so, so how do you infer these from the CMB given this model? So to start, let me say, how do you infer the matter density? So here's an only slightly cartoonified version of the CMB power spectrum, the temperature spectrum. So in blue, you see the actual temperature spectrum itself that you're familiar with. And actually, to get at the effect that I want to highlight, I have to take out a different effect that I'm sort of not interested in for the purposes of this talk, which is the CMB damping, which is the fact that really small scales in the CMB are damped away because actually individual photons on such small scales just had time to diffuse and mix together between the Big Bang and CMB last scattering. And also the fact that the width of the CMB last scattering surface has some finite width that is also averaged. And both of these smear power and smear the CMB and reduce power at small scales. And that's the damping, which in the red line that you see here has basically been artificially removed using a fitting formula. And that leaves you with the red line, where you can now more clearly see the effect that's interesting for the matter density, which is the so-called matter envelope. And that's the fact that there's sort of, now you can much more clearly see the nearly scale invariant spectrum that you expect from inflation. But also you see the fact that there's kind of this envelope. So at very, very largest scales, there's a little deficit of power, and then it sort of asymptotes to constant power at smaller scales. And this has to do with where in angular scale the era of matter redshift equality falls on here. And basically when you're at very small scales, which are modes that entered the horizon deep in the radiation dominated era, you just have this plateau. And for modes that enter during the matter era, you have this reduction in power, which is on the left of the plot. And the division between these, sort of where this envelope is, you can use to infer exactly when matter redshift matter radiation, the redshift of matter radiation equality, and therefore get what the matter density is. And the physical effect going on here is basically that the modes that enter the horizon and start oscillating during redshift, during radiation domination, basically receive a boost in power that the modes because of the radiation pressure of the plasma, whereas the other modes in the matter era don't receive this power. And so using this, you can sort of infer what the matter density is from the CMB. And so now how do you get the other piece to get h naught, which is lambda? So for this, you go to a different quantity in the CMB, which is very well constrained, and that's the angular size of the sound horizon, which is just basically the phase of those peaks. And this is essentially just given by these simple equations that you see here. So it's taking the distance that a sound wave traveled between the Big Bang and the last scattering surface, and just dividing that by the distance to the last scattering surface. And you can write these out as integrals over the in fact the inverse Hubble rate at these different scale factors A, and you get the equations that you see here. And so there's a couple of unknowns here. So the matter density we've already determined from this matter envelope effect. There's some dependence on the baryon density, which I'll mention in a second. There's a dependence on the radiation density in this piece here. But basically, if you measure the temperature of the CMB and you assume that it's a black body, then you know exactly the radiation density at all redshifts. Although I'll highlight that the later talk will actually discuss what happens if perhaps we don't know the exact temperature of the CMB. But for the standard lambda CDM model, it's essentially fixed. So this is not an unknown. The endpoint of this integral, basically when last scattering is, has very little dependence on any of these quantities. So that's actually essentially known. The sound speed, once you know the baryon density, is effectively known. And so therefore, if you had the matter density, which you know, this angle, which you measure very well, you could solve for what this lambda density is and therefore get H naught. So to do this, you just need this baryon density. And that actually also you can see in this picture, that's coming from this even odd peak height modulation that you see here, which has to do with the fact that actually these modes, this first peak corresponds to an overdensity, whereas this first trough corresponds to an underdensity. And actually the 0 point of the oscillator that are basically these modes in the primordial plasma is slightly offset. So the maximum and minimum aren't the exact same. And that offset has to do with the baryon density, which provides a pressure that creates that offset. So basically with all these things, we now have the matter density, this angle, we can solve for lambda, and we get the Hubble constant from the CMB. And you know, so sort of intuitively, that's what's happening. In explicitly in practice, you have a Boltzmann solver, you compute models of the CMB, you compare them to data, and you sort of do a Bayesian analysis, and that gets you the Hubble constant. But basically, circa 2014, you did this, and lambda CDM was looking pretty good. You had the results from the WMAP satellite, which measured the temperature and the polarization across the full sky. You were getting H naught of about 71. There were results from the South Pole Telescope on a smaller patch of the sky, but to much better angular resolution. And those were coming in at about 74. And you had results from some of these distance ladder measurements of H naught that were giving about 74. So probably, you know, if you guys were around back then, I was near the beginning of my career, but you looked at some of these and you sort of say, okay, lambda CDM is totally fine. H naught's probably like 73 or something, right? And then we got the Planck results, which showed us that H naught was actually 67. And this, I think, was kind of a surprise to a lot of people. I worked on Planck. I certainly remember the first time we sort of figured out this result and all the debates within the collaboration that you know, that took place, as people rightly so were you know, needed to make sure that this is right. But so what's the difference? You know, what's the cause of this? So looking at these two images, you see this WMAP and Planck maps. They certainly look identical, but you know, effectively Planck, the main thing that it adds is that it measured things to much better angular resolution. And that's something you can't see on this plot here. On this plot, maybe you can see things out to L, the angular multipole, out to about 100, just visually by eye. And all of the improvement of Planck is well above that. So you can't see it on this plot. So here's a comparison of Planck and WMAP on scales from 30 up to 12, about 1200. You see here in the top corner. So these are basically the scales where the two of them did measure the CMB basically up to the cosmic variance limit. And so basically each did equally well in terms of the cosmological information you could extract from this multipole range. And this is a comparison of those two maps you just saw. This is done by a bunch of authors that are actually in the WMAP, that were in the WMAP collaboration. And basically across this range, there's exquisite agreement. All these error bars are consistent with 0. They scatter the way that you think they should. And so the source of the difference between WMAP and Planck is not those scales. It's not the scales that both measured well, that they both measured well. It's actually this new information that was brought in by the small scales. And you can see this in the Planck data itself as well. So here are constraints on the cosmological parameters. The top row here is the 3 that I sort of just discussed in the previous slides. This other row are the other 3 parameters that you need to fully specify the standard model of cosmology, lambda CDM. And then there's sort of quote unquote derived parameters, things like H naught itself, which once you know the top ones, then you can figure out the bottom ones. And you can see that within the Planck data itself, basically, if you limit yourself to angular scales L less than 800, you get, with just the Planck data, you get, you know, H naught that's about 71, just like you did with WMAP. And then once you include the smaller scales all the way up to 2500 in temperature, which is basically as far as Planck can go, that's when you get this much reduced value of the Hubble constant. So what is it about this information at small scales that actually drove us to this shift? That's what I wanna show you in the next couple of slides. So so this plot, and I invite you to sort of try to familiarize yourself with it, as I'm going to repeat it over the next couple of slides. But basically, it's showing you. So this is angular multipole L versus a delta CL, a delta power, basically. And so this is the residual of the Planck data points to some fiducial model. The fiducial model here is one that's been fit just to the dark data point. So it's one that was fit just to the L less than 800 data points. And not yet been fit to these guys here. No, there's a Y-scale change. And also these arrows are to orient you. Those are where the tops of the peaks are in the CMB itself. And so right away, you can see that when you fit this model to L less than 800, and then you predict what the power should be at smaller scales, as you expect, it's not going to perfectly go through these data points. In fact, these residuals that you see here are what will drive the parameter shifts. If you're wondering whether these are okay, or whether right away this indicates a problem with the lambda CDM model, it does not. The chi-square of these data points to this model, which has not yet been fit to them, is essentially totally fine per degree of freedom. So let's now, or sorry, let me mention also that these features that you see, like the fact that the power here is a little high, then there's these oscillations. These were basically seen in all the Planck frequency bands, and so so that's a really good check that this isn't some instrumental systematic, which would be unlikely to be exactly the same between all these frequencies. Similarly, it's not some foreground, which you expect to vary with frequencies. So this is a very good check that sort of these features are real. So going back to here now. So now I want to fit a little bit more of the data and see what the model does. And so here I'm adding these new data points that are now highlighted darker. And as you expect, you can see the model goes up and grabs them. And, so what exactly actually happened? One way to understand that is if I break up the change in the model fit into the change due to first order individual delta parameters. And so then this gives me sort of a well-defined, like how much of this change is due to a change in the matter density or something. And that's what the colored lines now show. And you can see the legend here. And basically you can see most of the model change that went up and grabbed that first peak was actually just a shift in the theta, the angular size of the sound horizon, which is to say that the CMB spectrum basically stretched a little bit, and that gets you this. And that theta, that change in theta that causes you to get this, accounts for about 1 kilometer per second per megaparsec of the total downward shift of the Planck value of H naught. So let me actually now take this out of the whole plot. So I take out the blue curve out of the whole plot, so you can see it's basically being subtracted from the model and from the data points. And that's because I want to just look at now the remaining curves. And so now let me add a little bit more data, and again, let the model adjust. So you can see now it's sort of going to try and grab these low, high oscillations that are there. By the time I've added data up to about L of 1500, the whole model change is basically set. So these very last data points don't do very much. But but the remaining change you see is basically the fact that it grabs these wiggles, and the way it does so has to do with this sort of offsetting contribution from the smooth orange line, which is a change to the primordial power spectrum, AS and NS from inflation, and a change in the matter density, which is exactly a change in this matter envelope that I was describing before. And together, these give you something that doesn't have an offset, but has wiggles which match what the data apparently wants. And this change in the matter density is what gives you the remaining 2 or 2.5 kilometers per second per megaparsec reduction that brings you down all the way to the Planck value of 67.3. So, did I go over this? Yeah. So I should say also, it's not just the CMB which prefers a low value of H naught. Using the same sound horizon scale, but imprinted at later times in the galaxy distributions or in the Lyman alpha forest, you can also infer the Hubble constant, and it's kind of the same idea. So you have this angle now, which is the BAO angle, which is still an RS over a distance, but it's the distance to the BAO as opposed to the distance to the CMB. You have these similar integrals to compute these angles, and so now you don't want to use the CMB matter envelope effect to measure this matter density because maybe you want to just use the BAO. But it turns out that if you have enough different BAO types of BAO at different redshifts, and also you have the line of sight versus the perpendicular size of this feature, you basically can break enough degeneracies in this omega matter, omega lambda plane that you actually can get quite tight constraints on the Hubble constant from just BAO, supplemented with some BBN measurements to constrain this baryon density. But it's interesting because here, like in the CMB case, you have assumed lambda CDM holds in the early universe, and you get a low value of H naught, and this is kind of curious and is leading into the next couple of slides of my talk. There's one of what I know, there's one outlier in this story that with early universe you get pulled to lower values of the Hubble constant, and that is actually when you actually add the power spectrum of cosmic voids to this, which actually you end up with a data set which is independent of the CMB but still uses the early universe, but actually the voids pull you to slightly higher H naught. So this, I think, quite an interesting analysis, although statistically it doesn't quite pull you all the way. But basically what we're searching for is in this constraints on H naught, where the Planck values are very low here, we need to move them up with a cosmological model that takes us perhaps to 73 or 74. We basically want model X. That's what we're searching for. And the goal of such a model X would basically be that it restores concordance. It would be nice if it were compelling and beautiful. It'd be even nicer, perhaps, if it made predictions which we could go out and test. And so what could this model X look like? So that's what I want to spend my last couple of slides on here. And basically the point I want to make is that this model X is going to have to involve modifications to the very early universe between the Big Bang and last scattering. And I'm actually going to do it with sort of a proof of contradiction, where I'll try to make zero modifications whatsoever here and only modify here, and we'll see it doesn't really work. And this will be a totally general sort of discussion. And for example, I think in the next talk you'll hear more about more specific ways that you might do something like this. But so if you want to modify just late times and solve the Hubble tension, you probably, you might look at a plot like this, which has these BAO data points calibrated to Planck, and hence letting you constrain the Hubble rate as a function of the redshift of the BAO. Here's the high Reese value, and you look at this and you think, like, what are these idiots doing? Why don't they just make a model that like does this, right? That just hops up at the very end. It doesn't change the BAO, doesn't change Planck, and just grabs that Reese data point. And it turns out you can't really do this because there's a bunch of measurements of supernovae exactly in this redshift range that you would want to turn up the expansion rate very quickly to grab the data point from the distance ladder. And these supernovae, although they don't measure the absolute Hubble rate, they do measure its slope because they're standardized Hubble candles. And they just don't let that slope turn up fast enough. So that doesn't really work. And this has been basically checked by lots of groups that have tried to add different fitting functions for how to turn up the model. We did a paper where we used a spline fit to try to let the model turn up as fast as we can. And the plots you're seeing here are basically best fits that have been fit to the BAO and the supernovae, and that green data point here. And you just see that it is not allowed to turn up fast enough. So the other thing, in the interest of time, let me quickly skip this. So the other thing you could try to do is, well, actually, these BAO data points can only constrain H0 once you calibrate them. In this case, this was done with a CMB. But actually, with a different calibration, this whole thing can move up and down. And this calibration is basically the physical size of this sound horizon, which the BAO are measuring the angles of, or the delta redshift of. And if you change this away from the Planck value, so the Planck value is somewhere like 147, but if this were, say, like 139, then actually this low redshift picture becomes totally consistent and nice. And so you need about a 7% reduction. So the reason that this works is basically because, you can think of, for the simplest case is actually the measuring the line of sight BAO, where you're measuring the delta redshift between a galaxy that's sort of on the front and the back of this sound horizon perturbation. And that delta Z ends up being related just to RS times the H of Z exactly at that redshift. And so if you measure this delta Z very well, then you essentially can constrain the product of RS and H0, given that you interpolate back to H0 today using something like one of these spline fits. And that basically leads you to make plots like this one that we made, which is showing that in terms of H0 and RS from the BAO and supernovae, there's very tight and very model independent constraints in this plane, because we just sort of assume the spline fit. We don't have to assume lambda CDM, and we can get curves on here that look like this. They intersect the curve from just a direct constraint on H0, and the Planck value is here. And so what we need to do now is to reduce RS by 7%. This makes it obvious that you need to reduce RS by 7% to take you to this region here, so-called model X, which would restore concordance. So I just have 2 slides left, so I'll go through them here. I'm almost done. But how do I reduce, so this is sort of the proof by contradiction part. So how do I actually reduce RS by 7% in lambda CDM? So this is again the same integral you saw that gives you this quantity. So basically the radiation density, that's not a free parameter. The sound speed is hard to change by enough to get the 7% reduction. Really, the only thing I can do is increase the matter density by 7%. Sorry, by 30%, because it's here in the square root and it's in the integral. And I need to reduce RS by 7%. So if I reduce the matter density by 7%, by 30%, I can decrease this RS by this 7% I needed. But I've got to keep this angle constant, which means I have to decrease the distance to the last scattering also by 7%. And if I decrease the distance by 7%, I possibly have screwed up another quantity, which is the angular size of matter radiation equality, the thing I talked about at the very beginning of the talk. So I've decreased that by 7%, but there's no free parameter left, so the physical size of matter radiation equality will just change according to whatever change I made to the matter density, and it turns out that this will decrease by 30%. And so I will basically drastically have changed this angle, which is otherwise extremely well constrained by the CMB. Here's a bunch of constraints on this, given a bunch of models. And if I actually change this by the 23% or so that you get here, you're sort of it's not going to work. And the only way that such a solution that could work would be if something has confused the determination of this angle from the CMB. Then maybe I could have just a late time solution. And thinking about the kinds of things that might confuse the determination of this angle from the CMB, there's actually not that many late time effects in the CMB that really could screw you up. It's mostly just a projection. There is early and late time ISW. This will be relevant also for changing the temperature of the CMB, but in polarization, there is no ISW, and even polarization gets you a low value of H naught. So this seems unlikely to be a culprit. There is some impact on the CMB from reionization, but it turns out that you basically would need an even lower optical depth to raise the Hubble constant, and so that doesn't seem to work. Lensing is a late time effect that could confuse things and allow this value of theta eq to be, in actuality 20% lower. But this just seems unlikely because the reconstructions from the 4-point function of the lensing are basically very consistent with the expectation. It seems like it's all hanging together. And so basically you reach the conclusion that you can't really do it. You can't only modify lambda CDM here and reduce this RS by 7%. You have to do it by actually modifying the early universe. And since I'm basically out of time, I'll sort of just highlight that as a main conclusion of this part of the talk, that it does seem like things are pointing to that you need a change there. If you want, you can ask me about even more specifically where the change might be. That's this plot. And to conclude, I would just say that an important thing is that when you consider models, cosmological models that might resolve the tension, it is very important to consider all of the CMB, BAO, supernovae, and local measurements. The tension is sort of inherent in all of these, and if you just pick 2 out of 3 or something, there's many examples of models that work, but that don't work when you consider all of them. And also to say that there's a bunch more relevant data coming soon, things from EBOS, better BAO, there's better CMB measurements from the Atacama Cosmology Telescope, SPT3G, and eventually stage 4 CMB and galaxy surveys that should shed more of a light on this whole issue. So I'll stop there and sorry for going a little over and take any questions.
Thank you for a nice talk. So we have time for a few questions, please. All right, looks like there are no questions yet. So maybe there is a question from Vivian Pulan. Yeah, okay, of course you can type, I can read it.
Yeah, actually with my screen shared, I don't see the chat, so if someone can relay the question to me.
So Vivian Pulan is asking, do you see a possible relation between these tensions and a lens?
Yes, so there very much is a relation. And let me go back to here.
Given the internal inconsistency of Planck.
That's right. So yeah, so this A lens thing is basically the Planck temperature peaks look a little like the model wants them to be even more smoothed than, sorry, the data wants them to be even more smoothed than the model allows it. And it's actually, you can really just see it by eye on a plot like this that I showed you. The data seems to want this oscillatory residual where the value at the peak is lower and the value in between the peaks is higher. And the model does kind of fit that, but it turns out that if it could, it would take even more of that effect. And if you sort of artificially allow yourself to just have more lensing, and the model can fit these oscillations with lensing, and it doesn't have to fit it with these shifts in the matter density like I show here, and therefore you get a little bit higher H0. But ultimately, I've not found, the problem is just that this isn't a physical model, and physically from the 4-point reconstruction of the lensing that I mentioned, that the lensing amplitude is very near 1. It doesn't appear to actually be high. So this doesn't actually appear to really be lensing. And so it doesn't pave the way for cosmological solution in that sense. So it seems like it's probably either just like a 3-ish sigma fluke in the data, which it very well could be. We looked at this data in 100 million different ways, and maybe, you might find a 3 sigma fluke. Maybe there's some small residual systematic, but even that seemed less and less likely to me as more and more people poured over this. It's also present at some level in the different frequencies. So I'm not sure. It could play a role, it could be a light hint of something, but it's not at the significance that you would know for sure, or it could just be a minor fluke.
All right, thanks. There are a couple of more questions in the chat. So first, Divya from Divya Chakraborty, do you have any comment on the early dark energy models as a way to modify early universe?
Yeah, so if I had time to say it, I think they're basically exactly the type of solution that what I argued here points towards, where maybe I can use this as an excuse to show this slide that I didn't have time for. Well, no, it'll take too long to describe this, but basically, I argued that the solution seems to want to be in the early universe, or at least that's one easy way to do it. And these early dark energy models that basically, they have this extra energy density that contributes, increases the expansion rate, reduces RS by, say, approaching that 7% that you need to get full consistency. It does seem like a natural way to do this. Now, these models aren't perfect themselves. They don't get you all the way. They're not completely allowed by all the different data sets that are there. So it feels like I haven't seen like the absolute slam dunk solution using these models, but it very much seems like the kind of thing that's on the right track.
All right, very fast. The last question from Sandipan Sengupta. Can matter with some higher equation of state and radiation before radiation domination solve existential potentially? Can you comment very fast?
I think the answer is probably maybe. If it's changing the expansion rate near matter radiation equality, then yes, that's the kind of thing that could resolve this. So let me just say that. All
right. Thanks again for a nice talk. So let's move again.
Thank you.
Let's move on to our next speaker, who is Alessia Notari. So.
Yes. So